Hello, everybody. I'm Delimpaltadakis from Delft University of Technology, and today I will talk about traffic abstractions of homogeneous event-triggered control systems. In network control systems, the main sampling paradigm is periodic sampling. And the good thing with periodic sampling is that scheduling communication traffic becomes an easy task, as the sampling instance of control loops in the network are known a priori. Now we know that event-triggered control has been proposed to tackle the sampling inefficiency of periodic sampling, but it still remains a question: is scheduling easy or even possible now that the sampling instances are unknown? The main approach in the literature for traffic scheduling in networks of ETC systems is the co-design approach. According to it, we co-design the controllers, samplers, and the scheduler in order to avoid packet collisions in the network. Unfortunately, it is a non-versatile approach because, for example, if a new control loop joins the network, the whole design process has to be applied from scratch. An essentially different line of work is abstraction-based scheduling, which decouples the designs. In particular, it assumes that the controllers and triggering conditions have already been designed independently, and it abstracts the system's sampling behavior. Finally, it uses these abstract models, these finite abstractions, to derive a traffic scheduler. Now, this approach is actually versatile because even if a new control loop joins the network, the controllers and triggering conditions do not have to be designed again, and the abstract models remain the same. But how does a traffic abstraction look like? You can imagine it as a finite state machine, and each state of the machine corresponds to a region in the state space of the actual ETC system. To each region, we associate an interval which gives us the expected intersampling time, provided that the previously measured state belonged in the corresponding region. Finally, the transitions indicate the location of the state after an elapsed intersampling time. So, for example, if at sampling time Ti the state belonged in R1, then we know that the next sampling time will be from 0.1 to 0.2 time units from Ti, and that the next sampled state will either belong in R2 or in R3. Now, traffic abstractions have already been derived for LTI systems in previous work, where the regions were cones pointed at the origin, the intervals were computed via linear matrix inequalities, and the transitions via reachability analysis. Our problem statement for the day is to construct traffic abstractions of homogeneous systems. And the motivation for why we focus on homogeneous systems is the homogenization procedure, which has been proposed in this reference here, and might render our approach applicable to general nonlinear systems. A bit of a theoretical background, so consider an ETC system where we denote the sampling times by Ti and define the measurement error epsilon. Now we know that the dynamics of the state and the measurement error can be written in this compact form. At sampling times, the state of course remains unchanged, but the measurement error resets to 0. The sampling times are defined as the times when this function phi, the triggering function, becomes positive, and we denote the intersampling time by tau. Each point in the state space of the system corresponds to a unique intersampling time. Finally, a function f is called homogeneous of degree alpha if it satisfies this scaling property. Observe that for alpha 0, we recover linear functions, basically. To formalize our problem statement, given an ETC system of which the vector field is homogeneous of degree alpha greater or equal than 1, and given a homogeneous triggering function phi, we have to construct an abstract model with the regions again belonging in the state space of the system, and the I, j subscript will become clear later on. We have to construct the intervals that bound the intersampling times of the regions, and finally, we have to determine transitions Ri, j to k, L, which are defined if there exists at least one trajectory starting from Ri, j that lands in Rk, L at the intersampling time tau of x. Now a hint, for the lower bounds on intersampling times and the regions, what we will do is we will fix sometimes tau lower bar to serve as lower bounds on intersampling times, and then we will find regions Ri, j in the state space that satisfy this part of the inequality here, so that tau lower bar is a lower bound on intersampling times. Then, given these regions, for the upper bounds and the transitions, we will conduct reachability analysis. So, for the regions and the lower bounds, first, we arbitrarily choose an ordered finite set of times tau I to serve as lower bounds on intersampling times. Then, in a previous work of ours, for such a set of times, we have derived some isochronous sets Ri, for which the intersampling times of all points in these sets are lower bounded by tau I. These sets, you can see an example of them in this figure here. Now you could think that we could actually stop here now that we have recovered the inequality that we were looking for. However, these sets are actually very big for reachability analysis purposes, so we chose to further divide them by cones Cj and obtain their intersections with these cones Cj as our regions Ri, j. Then we have that the lower bounds on intersampling times for these regions are the times that we have selected, tau I. Another problem that we encountered while trying to conduct reachability analysis on these regions is that they obtain a transcendental description due to this function mu. So to solve this problem, we managed to over-approximate these regions by ball segments R hat I, j, which you can see here in the figure, for example. How did we do that? We devised an iterative algorithm that performs a line search on the inner and outer radius of the ball segment to be found. And this algorithm checks iteratively if these conditions hold. It performs these checks via an SMT solver, which vaguely is a tool that is able to answer yes or no to such questions. Now, for the upper bounds on intersampling times, we consider the dynamics of the ETC system, and we define a set of initial conditions for reachability analysis to be our state initially belongs in the ball segment over approximation, and the measurement error is initially 0. We also define a set U to be the set of combinations of the state and the measurement error for which the triggering function is negative. Then we perform a line search on the upper bound tau over bar until there is no trajectory starting from I that at time tau over bar is in U, which would imply that for all trajectories that start from I, the triggering function is positive at time tau over bar, which in turn implies that tau over bar is an upper bound on intersampling times of Ri, j. Of course, this condition here, we check it via reachability analysis tools. Finally, for the transitions Ri, j to k, L, we take the zeta part or the state part of the already computed trajectory flow pipes, and we check if within the interval of intersampling times, it lands in r hat k comma L. And if it does, then we define a transition. Now a numerical example. Consider a 2D system, which is homogeneous of degree 2, and the triggering function, which is homogeneous of degree 1. We choose this set as the set of lower bounds on intersampling times, and we divide the isochronous sets Ri by 16 cones. The created partition, you can see it in this figure here, and the red lines delimit the ball segment over approximations of the regions Ri, j. We could actually say that they are relatively accurate over approximations. On the figure on the left, you can see the lower and upper bounds on intersampling times for each region, and the figure on the right depicts transitions between the regions. We observe that all regions R3, something obtain transitions between each other, but this was to be expected because, as you can see here, they all intersect at the origin. To conclude, we have constructed traffic abstractions of homogeneous ETC systems, thus extending the abstraction-based scheduling framework from LTI to homogeneous systems. We actually used a different approach than the previous work on LTI, specifically in determining the regions and the associated intervals. Now, our hopes of potential extendability of our approach were actually valid, because in a subsequent paper of ours, which is currently under review, we managed to extend our approach with slight modifications to general nonlinear systems with disturbances, uncertainties, and general triggering functions. Finally, some challenges ahead that we will try to tackle is the curse of dimensionality that is inherent in our construction, and also our construction's non-determinism. Thank you for watching.